In the previous subsection, we've seen some immediate applications of suffix trees to solve various strings problems. It turns out for various other problems, you need a little extra information. The suffix tree alone is not quite enough to solve these, and what we need in addition are these longest common extensions. The suffix trees are a key step to efficiently answer such queries, so it will build on suffix trees and use these as before, but a little additional step can boost their power substantially. So what are these longest common extensions? It's a problem of independent interest, but we'll see more specific use cases of it. It's the following problem. You're given a string, as always in the last couple of units, right? And we want to answer these LCE queries, longest common extension queries. So what are these queries? Here you're given two positions in the text. So as always, I like to draw these pictures to make things a little more graphical. You're looking at two positions in the text. And now you'd like to know how far can you jointly scan to the right where you see the same string. Okay? So formally, LCE of two positions I and j is the longest extension. It's the maximal L so that the length L substring starting at I and starting at j of t are equal. Okay? But imagine you have two pointers that look at these positions I and j, and you ask how long can you move them to the right in lockstep before you find different characters. That's the longest common extension problem. It turns out the information we need to solve this problem is already contained in the suffix tree. Clearly, any two positions in t correspond to a suffix starting at this position. So the longest common extension of I and j in t is nothing but the longest common prefix of two suffixes, namely the suffix starting at I and j. Again, if you look at this picture, if you start at I and j, if you take the suffix starting here and the second suffix starting here, well, clearly the longest common prefix, the longest prefix that these two suffixes both have in common, that's nothing different than this longest common extension. It's just a different way of asking for it. Maybe formally we should say the length of this thing. The longest common extension really is an integer. It's the length of this extension. And well, maybe depends on who defines it. Here I defined it as the length. Sometimes people also use the actual string. Let's leave it at that as that. So the confusion I'm mentioning is both longest common prefix and longest common extension can either be the length of these shared strings, or it can be the string itself. Depending on the application, one or the other is more convenient to use, but it's really the same thing. If you have the length, you know where it starts in the string, so it's just the substring starting at that position. So we already know what this is. It's the same thing, just a different name for the longest common prefix of two suffixes. And that again was, remember, we used this before when we were talking about the longest repeated substring. That is the string depth of the longest common ancestor of I and j. I mentioned the term at the time already. So if you remember, the example there was we had ban, A-ban, and we had an, and we were asking for the longest common substring of these two. And we found that this was just the A, and the reason is that we would walk a ban to this leaf and a an to this leaf, and the lowest common ancestor of these two leaves is this node. That's the last node they have in common when we walk the root to leaf path. So in short, and this is really highlighted here because you should remember this. We'll review it after Easter, but we'll use this later on. The longest common extension of two positions, as we've just argued lengthily, is nothing but the longest common prefix of these two suffixes. And that is the string depth of the lowest common ancestor of those two leaves with the given indices. So you see, in all of these three terms, the numbers I and j are involved. Either it's the starting positions in the text, or it's the starting positions of an index of a suffix. So it's the name of a suffix, if you like, or it's the name of a leaf, but it's really the same numbers in all cases. So do remember this one. We'll come back to it after the Christmas break. How can we answer these LCE queries? We could do simple things. We could start at the leaves and walk up the tree until we find a common node. That is possible, but it can be slow. In the worst case, you have to walk through the entire tree, and there's no bound on the height of a suffix tree better than linear. The other option would be we pre-compute all the possible LCAs, LCEs, longest common extensions or lowest common ancestors. We can pre-compute all the lowest common ancestors in a big table, but that table is very big, so even just writing it out to memory would take quadratic time, and that again is not interesting for the problems we have. We can't afford this. Again, an amazing result is that you can compute a data structure in linear time and space, and then after that computes the lowest common ancestors of any two leaves in constant time. It's just blink of your eye and you get the answer. This one is a little tricky to understand, but if we have time at the end of the module, I want to introduce you to how to do this, even though it will not be part of the exam material. Again, clearly a theoretical breakthrough, but also useful in practice because there are implementations that do this very efficiently. And so this has again been, together with suffix trees, these two things are game changers in stringology. For now, we'll treat the construction of this data structure for lowest common ancestors as a black box. So you may remember this. After linear time pre-processing, we can compute the suffix tree and the lowest common ancestors in the suffix tree. And that together gives us the longest common extensions in a string in constant time after the pre-processing. And this is something you can use for even more interesting problems like this one. That's the approximate matching problem. Remember, so far we were given a text and we were looking for exact matches of our pattern in the text. Often this is a little too strict, especially if humans type the patterns. So here we're given a text and a pattern, and additionally a parameter, a number k. And we're now interested in a match, well, the first match again, where the part of the text and the pattern don't have to be exactly the same, but they have to be within Hamming distance of k. And so Hamming distance, that's just counting the number of mismatched characters. The number of positions where the characters are different. Okay. If there's no such match, no such position where we can find something within Hamming distance k, then we report no match. Otherwise, we report the first occurrence. So in a sense, it's like searching with typos. You can substitute one letter for another, and it will still find the occurrences in the text. Okay. What we'll do here is we do a similar trick as for the generalized suffix tree. We take the text and the pattern and make a single string out of it, but we separate it with dollars so that we know when these things end. And now we construct the longest common extensions on this combined string. And you can basically do this. you build the generalized suffix tree and then compute the lowest common ancestors in the generalized suffix tree. So this is going from one string to several strings is again with similar tricks as we've seen for the generalized suffix tree is again possible here. So we can use longest common extensions also in different strings, and it works in essentially the same way.